Hi again, everybody, and welcome back. So example 9.8 is it's really just a momentum problem, but it's a momentum problem in two different directions. We have two objects that, well, let me back up. It's a collision problem, too. It's certainly an inelastic collision where we have this car moving this way and this car moving this way, and then they collide and they kind of connect and wrap around each other and become kind of one mass, and then move off in some unknown direction at some unknown velocity, which is what we want to find. But since with inelastic collisions, energy is not conserved, we have to solve this using momentum. The only difference between this and the other momentum problems is that, like I was saying before, we have this in two different directions right here. The one car is moving in the x direction only, with a velocity and a mass, and the other car is moving in the y direction only, with a velocity and it has a mass. So all we're going to do initially right here is we're going to write down the values of each car, the velocity and the mass, and then I'm going to shrink this down, and so we can actually have a little bit more space to solve this. Real quick, the plan of action here is to solve for the final momentum, breaking everything down into the x direction only. Oops, didn't mean to do that. Into the x direction only and the y direction only, and then recombine those components of the final velocity and the direction, very much like we did using vectors. Okay? So we have a car. The orange car is, let's see if I can do that. We'll call it red, so we'll draw it in red, is 950 kilograms. Okay, so mass of the car is 950, and the initial velocity of the car, draw this again, initial velocity of the car in the x direction only, that is 16 meters per second. Okay, 16 meters per second. By the way, this direction is positive x, as indicated by the axis right there, and this direction is positive y, as indicated by that axis right there. All right? We also have a minivan. And so the minivan, the mass, mm, is going to be 1,300 kilograms. 1,300 kilograms, and the initial velocity of the minivan in the y direction, or the y hat direction, is 21 meters per second. Okay? So that means that this, the initial velocity of the car has no initial velocity in the y direction. So we can say it's this right here plus 0 meters per second y hat. Well, that's kind of assumed right there. And the same thing is true of the x direction of the minivan. So it's this velocity plus 0 meters per second x hat that the minivan has. And so when we add the x and y components and find the total, the final momentum, we're going to be dealing only with one direction for each of the two cars, at least initially. Okay? So we have all of our stuff written down, and let's write down our basic equation for solving for momentum in any one direction. Okay? And that is, I'll write this at the bottom right here. I'll write it in black, and then we'll shrink it down. Mass times mass of the car times velocity of the car plus mass of the minivan times velocity of the minivan equals mass of, what are they after the collision? Well, they're one big mass, right? So it'll be mass of the car plus mass of the minivan, that added mass, times the final velocity of that system, which is what we're trying to find. Okay? And the problem is we'll have to do this in pieces because we can't do it all in one direction because they're not going one direction initially. They are afterwards. Okay? So let's shrink this down, and let's solve initially just for our x direction. All right? I usually like to do the x direction in green. All right? So all right, so for x hat direction right here, what can we say? Well, we have the initial velocity of the car, right? So So this is just the x hat direction. It's not part of the equation right there. Times the mass of the car. So we've got our initial momentum of the car, the red one. So it's mass of the car times initial velocity of the car, x hat, right? Plus mass of the minivan times initial velocity of the minivan, x hat. Wait a minute, what's that? That's 0, right? So that goes away anyway, because right here, our initial velocity in the x direction of the minivan is 0. Equals the mass of the car plus the mass of the minivan times final velocity of that system, car and minivan, x hat. Okay, so that's going to solve for the final velocity of the system in the x direction. Let's do the same thing for y. All right, in the y direction, we have, and I'll do it in the same order, mass of the car times initial velocity of the car, the red car that is, in the x hat direction. Wait a minute, that's 0, right? I'm sorry, we're doing y, right? In the y direction. And as I mentioned before, that is 0, so that goes away anyway. You didn't really need to write that, but I am drawing it to account for it. Plus the mass of the minivan times the initial velocity of the minivan, which it definitely has an initial velocity, y hat, right there, equals mass of the car plus mass of the minivan, so it's the final mass of the system, times final velocity of the system, y hat, instead of x. Okay? I still don't think I left enough room for myself, but that's all right. We'll figure it out. So, we are solving for what? Well, we're solving for this final velocity of the whole system going up at some magnitude and at some angle. All right, well, we're going to need to find the final velocity in the x, which is right here, and the final velocity in the y direction, which is right here. So we're solving for this guy and for this guy. All right? So shrink it down a little bit even further so I have some more room. So for the final velocity of the system in the x direction right here, what am I going to do? Well, that goes away. So I'm going to take this, mass of the car plus mass of the minivan, and divide it down below, mass of the car times the initial velocity of the car in the x direction. So for the final velocity of the system, x hat, that equals mass of the car times initial velocity of the car, x hat, all of which we know, divided by this stuff right here, the combined mass of them both. Mass of the car plus mass of the minivan. We do the same thing for the y. All right? Final velocity of the system in the y hat direction. That's going to be what? Well, again, this goes away, so we don't need to worry about that. We're going to solve for this by dividing this down. So that's going to go down below mass of the minivan times initial velocity of the minivan in the y direction. So mass of the minivan times initial velocity of the minivan in the y hat direction, divided by the combined mass of them both, because that gets divided down. So mass of the car plus mass of the minivan, it's a terrible M, and that's going to be our final velocity in the y direction. All right, well, let's put our values in and see what we get. Mass of the car, that's 950, right? 950, yes. 950 times initial velocity of the car, that's 16 meters per second, right? I'm leaving my units out just for clarity's sake right here. Divided by the combined mass of them both, so that's 950 plus 1,300. All right, I'll write down my y as well, and then we'll calculate them both at the same time. Y is going to be, what's the mass of the minivan? 1,300, right? Times initial velocity of the minivan in the y direction, that's 20, it's not a 2, 21 meters per second, divided by the combined mass of them both. 950 plus 1,300. And that's going to give us our V final in the y direction. All right? Let's find our V final and the Y. So I've got 1,300 times 21 divided by the sum of 950 plus 1,300. I get 12.1 meters per second y hat that system is moving. All right, how about in the x direction? Well, let's see. For the x hat direction, I get a total of 6.76. So this is going to be green. 6.76 meters per second x hat. Okay? So those are our final components, or I should say those are our components of the final velocity of that system right there. Now all we need to do is just combine them. So I'm going to do that kind of up at the top right here. I've been shrinking this down smaller and smaller. I think we can take this and combine them, right? So I'm going to write this in red. So we want the full magnitude of the final velocity. So the magnitude the final velocity of the system is going to be the square root of, because we're using a Pythagorean, right? 6.75 squared plus 12.1 squared, right? 6.75 squared plus 12.1 squared. And I'm also going to write out our equation for our angle, right? Because we want not just the magnitude, but also the angle theta from the horizontal right there. So for the theta of the final velocity, how do we get that? Well, that's the inverse tangent, right? Inverse tangent of y over the x, right? So it's 12.1 over 6.76. And that's going to be our direction. So let's find our magnitude, all right? So 6.75 squared plus 12.1 squared, square root, 13.9 meters per second. That's our final velocity of the whole system. At what angle? When we do the inverse tangent of 12.1 divided by 6.75. 60, round it to 61 degrees. 61 degrees north of east or above the positive x-axis, however you want to say it. All right, so there you go. There's our final magnitude and our final direction. We used conservation of momentum to figure out what the final momentum was in each direction, then simply used our knowledge of vectors to combine those two components and get the full magnitude of the whatever direction and speed the cars are going after having collided and stuck together. All right, so that's example 9-8, a good two-dimensional momentum problem. Thanks for following along. If you have any questions, come see me. But in the meantime, thanks for following along.